Hi everyone. Today we are tackling some classical open channel flow problems that can come in your midterm or in the fundamental of engineering exam as well. So before we start, previously as well, I would like to introduce some of the key concepts that we are going to use in solving today's four problems. So first one is hydraulic element graph. Uh, Most hydraulic formulas like many equation are easy to solve when a pipe is 100% full, but in real world, like in the later questions, we will be using sewers or storm drains. They can cover just maybe 40% or 30% full of pipe. So this graph help us to um, compute the value that can be used while interpretation of the depth to diameter as well. And let me explain the axis. The vertical axis is a ratio of flow depth diameter. If your pipe is 2 feet wide, that is diameter, and the water is 1 foot deep, D, your ratio will be like zero point 0.5. Similarly, for horizontal axis, this represents the ratio of the element. It goes from 0 to uh, here 1.3 in this case. This tells us what percentage of the full capacity we are actually using. So this curve help us to find the discharge curve, that is Q actual by Q full, velocity curve, that is velocity actual by velocity full. Similarly, for area as well, we can compute that. Similarly, like I already mentioned, so we can use these tricks to read the above chart. So I will not go on detail. And in one of the question as well, there is slightly confusing terms, so I talk them first before introducing them. Uppercase Q, it means the total flow of the whole river, which is discharge, whereas this lower Q, it means the flow for 1 foot slice. And for question number four, I received some of the questions as well about the taking the positive or negative sign. So if you use the resultant force caused on force exert on the wall or ramp, that is positive. If you take positive in the equation and suppose you got your answer positive, then the force is downstream, whereas if your answer is negative, then force is upstream. Similarly, if you use negative sign for force, then if you got like answer positive, then force is upstream, and similarly if you got the answer negative, then force is downstream. So, since we are dealing with hydraulic jump, we also recently saw or conducted the lab about hydraulic jumps. So it always goes from the shallow, that is supercritical, to deep subcritical, while like smooth transition through critical depth like M2 or S2 usually happen at slow breaks or drop. So for water surface profile, so one of the few important things that I want to emphasize is water always try to reach normal depth. It's the equilibrium, and water cannot cross critical depth smoothly. It either jumps hydraulic jump or passes through at a control point, that is dam or channel break, like mild slope to steep slope. And for zone 1 curves always go from normal, depth increases. Zone 2 curves approach critical, zone 3 curves approach normal. And for dam or reservoir, so they are typically type 1, so they cause backwater effect. And drop or transition, which is also considered as type 2, it draws water down. And gates like sluice gate, it is considered as type 3, force water thin. And last fifth one is subcritical flow, where y is greater than critical depth, is controlled from the downstream. Supercritical flow is y is less than critical depth, which is controlled from upstream. So to check the mild or steep slope, so I have written here the some easy way to remember. Like for mild slope, I have drawn normal depth as well, critical depth as well, and we can consider this black line as gentle slope or water moving slowly. So first one we consider as zone 1, and second zone 2, and third zone 3. So if normal depth is greater than critical depth, then we consider that as mild slope. Whereas for considering steep slope, if the critical depth is greater than normal depth, then we consider that as steep slope. And like if we compare actual depth y to yn and yc, then if y actual depth is greater than both yn normal depth and yc, then we can consider that as zone 1, which is like m1 or s1. Similarly, if the actual depth is between yn and yc, then we consider that as m2 or s2. Whereas for zone 3, uh, y should be less than uh, normal depth and critical depth. So our step will be first checking whether the profile is mild or steep, and from where it goes, where is the water, like in which zone 1, zone 2, zone 3, and what cause it, like dam or reservoir push water up above normal, which is type 1, and free drops and steep transition pull water down, which is type 2, and gates force water below both line, which is type 3. Now let's go to question number 1, which asks us to label each section of the channel as steep or mild, and it says water flows from left to right, and we need to draw water surface profile and label the curve, that is m1, s1, etc. So example is given, and for the first problem, so upstream of gate 1, so we will be looking at this part first. So channel yn is greater than yc. So here gate 1 is downstream obstruction that backs water up above both yn and yc, which is considered as zone 1 m1. So that is this curve, slightly curve, is known as also backwater curve. So depth increases at water approaches the gate. And after gate 1 on steep section, so yc is greater than yn, so it is considered as a y1, and gate forces water thin and fast below both yc and yn, which is equal to zone 3 and zone 3 or s3, and water rises toward normal depth on the steep channel. And after it approaches this gate 2, it is still steep, so gate 2 is the abstraction, water backs up above normal, above both lines, which is called zone 1, that is s1 in this case, because it is on the steep, and depth increases while approaching gate 2. And for after gate 2, now we are in the mild channel. A gate forces water below both line, that is M3 or zone 3. This is supercritical flow on a mild channel. It must end in a hydraulic jump. So M3, it rises toward critical, then there will be hydraulic jump back to the subcritical. And after hydraulic jump, water is subcritical, sitting between YC and YN zone 2, and depth gradually increases toward normal depth going downstream. And now similarly for question number B, since YC is greater than YN, so it is steep slope and water is going downside, so it is S2 curve, and this point acts as slope break, or we can consider that as control segment. And here there will be M3, and before it breaks to critical depth, there needs to be some hydraulic jump. So there is hydraulic jump and creates a M2 curve. And after this break 2 as well, since the YC is greater than YN, it will be slightly this S2 curve. Now let's go to question number 1C. Here we can consider this as reservoir R, and the reservoir releases water at approximately YC at the channel entrance, and this can act as upstream control. It is not shown in the homework problem, but I just want to emphasize this as control, upstream control, and water then accelerate downhill, dropping from YC to YN. It's between two zones, zone 1 and zone 2. So it is called zone 2 and drawdown toward normal depth. So here flow becomes supercritical. And after this slow break, it enters into the mild zone, mild slope, and here there will be fast supercritical water from steep flow, which is below both YN and YC, and we call that as zone 3. And there will be hydraulic jump as the water can't cross this YC smoothly, so there should be some jump, and we also observe that in our lab as well. And after jump, water is subcritical, which is between YC and YN, and depth gradually increases toward normal depth going downstream. And after it reaches here, it's this surface is rough, so it has higher Mannings, and the rough section act like downstream abstraction, and it demands deeper flow. So water must rise above the smooth section YN to reach the rough surface YN, and this is above original YN zone 1. So here also there will be backwater effect. So it is considered as M1 surface. Now let's go to problem 2, which is related to hydraulic element chart that I discussed earlier. The question, let us read for first question. So 21-inch diameter sewer, we need to convert this into feet or meter, and this n is also given, and it carries 5 cubic feet per second, and it is laid on the slope of 1.5%, and what is the velocity in the pipe. So here scenario is like a sewer pipe isn't running full, and we need to find the velocity, find the actual velocity. So we will be using here Manning's equation for finding the Q full and velocity full, and let us like rewrite the given terms. First, it is given like diameter is 21 inch, so we convert that into 1.75, and this n is also given, which is 0.015. Q is given 5 cubic feet per second. Slope is 1.5%, which will be equivalent to 0.015, and we need to find velocity. So before we use many equation, let us calculate the area and weighted perimeter. So after we compute weighted perimeter and area, we can directly input in the Manning's equation. Since this is a BG system, so we will be using 1.49 for the km, and by computation we will have 16.94 cubic feet per second. And since our actual flow is given, and we also have like full full flow, then we can find flow ratio, and which will be equal to 0.29. Now let us like read from the weighted perimeter. So since our ratio is 0.29, so we will be using hydraulic property, and 0.3, 0.29 here. And when we horizontally align here, it will be around 0.38. So our depth to diameter ratio is 0.38, and when we align horizontally here, like it will be like our velocity ratio, which will be equal to 0.88. So we have d by depth to diameter ratio at 0.38 and velocity ratio at 0.88. So since we know the uh, full velocity, we can know the actual velocity as well. So this gives us 6.18 feet per second. So if you wonder how I calculate B for full, so I have used continuity equation. Q is equal to AB. So from that I have got 7.03. Also for 2B, let us read the first question. So question asks us about the finding depth and velocity of flow when a pipe is carrying 40% of the full flow. So here it is already a ratio of flow is given, and this sewer is like 18.8 diameter, and it carries when it runs full, so it can carry 6.2 cubic feet per second. So diameter is given, q is given. We need to find depth. We need to also find velocity. And since like we don't know the actual flow, we know the q flow. So when we rearrange this, when we solve this ratio, then we get like q half is equal to 2.48. And from graph, this B actual by V full will be 0.92. So I use this 0.4, and I computed like from here 0.4 to this discharge line. So it helps me to give 0.44 as D by D. And from that I use like here I got velocity. So that's how I got this V actual divided by V full. And since we have not computed the velocity for full flow, so let us do by the using the q by area. So our q is 6.2, and our area is given by pi by 4 times 1.5 square, so that gives us 3.5. And when I input this into this ratio, I will have b actual will be 3.22 feet per second, whereas d will be, because our ratio is given, we obtain from graph. So 0.44 times this d, which is equal to 1.5, so that gives us 0.66 feet. So let us start problem 3. So we have given like trapezoidal channel that has bottom width of 5 meters, side slope equal to 1.5, that carries 60 cubic meter per second at a depth of 3.2 meters. So we need to find four things: alternate depth for same specific energy, critical depth, and normal depth, and also finding whether the flow is getting deeper or shallower. So let's first establish or rewrite the geometric properties at our given uh, uh, depth of 3.2. So for a trapezoidal channel, a quantity equals B plus. So for a trapezoidal channel, area will be equal to B plus 2y times y, and which will be equal to 31.36 meter square. And we also need to compute this top width t, which will be equal to b plus 2zy, that gives us 14.6. It will be used in later part. And velocity is equal to q by a, so that gives us 1.91 meter per second. And hydraulic depth d, which is equal to a by t, that equals 2.1 meter, 15 meter. And now let us do alternate depth. So two depth can have same specific energy, one subcritical and one supercritical. These are called alternate depth. So first let us compute specific energy at y, compute specific energy at y is equal to 3.2 meter. So y is equal to y plus b square divided by 2g. So that gives us energy of 3.38 meter. Now we need to find another depth, y a, that is alternate depth, that can give us same specific energy of 3.38. So since 3.2 is 2 meter is subcritical, we will verify that shortly. And the alternate depth will be supercritical, meaning shallower. We set up like equation, same equation, like E is equal to ya plus q square divided by 2ga square. So here I just rearranging the same formula, but we are using q by a. And we don't know the value of a, so we need to do trial and error. So for this uh, for this problem, I have not shown the trial and error, but I directly computed ya is equal to 1.35 meter. So hence our alternate depth for semi specific energy is equal to 1.35 meter. And one of the tip that I can give for trial and error on alternate depth is start with a small value, since you are looking for the supercritical alternate, and bracket the answer. If uh, energy is too high, increase ya. If energy is too low, decrease ya. Now let us jump to find the critical depth, which is also similar to example 6.6 of book, since we know the equation, this 6.13, which is from book. So we know q square divided by g is equal to dA square. So this d uh, we have already computed. And so after this, like rearranging this equation in terms of a by t, so because we can compute the a and t easily. So our RHS or LHS will be equal to 366.97. And solving trial and error, that is, we don't know the critical depth here. So YC, we can put like 1.5 meter first and find the area, which will be B plus MYC bracket open close times yc, whereas for t it will be equal to b plus 2 myc. So when we compute area and t and just put in the a cube by t, we have for the first case of yc we get 136, and that doesn't meet our target, which was set as 366.97. And after increasing to 2, we get nearly 372.36, which is near. So we can, for now, we can consider that as our critical depth. You can use solver for more precise answer. And now it's time for computing the normal depth using Manning equation. And we are also given some parameter. S is equal to 0.004 and N is also equal to 0.022. So since it is given on meter SI unit, so Q is equal to 1 by N times A times RH uh, hydraulic radius to the power 2 by 3 times slope 1 by 2. So rearranging all these things, we get like 66 is equal to A times hydraulic radius to the power 2 by 3. Let us assume this as equation 1, and we can compute area. So for area of the trapezoidal uh, channel, so it will be B plus ZYN times yn, and our weighted perimeter will be b plus 2 yn root under 1 plus m square. So since we have area and perimeter, so we can compute hydraulic radius, which is a by p, and let us do some trial and error computation. So first I will start from 0.2. So it's just my random number, and I get when I use this yn as 0.2 in this equation to compute area and perimeter, I get for area is equal to 1.06, and for p perimeter, weighted perimeter, so I get 5.72. And when I compute RH is equal RH will be was like 0.18. And when I compute area times this hydraulic radius to the power 2 by 3, I get 0.34. So which is way less than this 66. So I increase it to directly 3, and I did the same process and it gave me 42.2. It is also slightly below than this 66. And again I did this is 3.76. So I did some internal hit and trial here, and to make it compact I directly choose 3.76, which I got through hit and trial, and it will be equal to 66.8. So which meet our target, like approximately met our target. So our normal depth will be 3.76 meter. And our fourth part is the depth getting deeper or shallower downstream. So let's line up our three depth. So our actual depth is 3.2 meter, and critical depth is approximately equal to 2 meter, and our normal depth is equal to 3.76 meter. And since yn 3.76 is greater than critical depth 2 meter, the channel is mild. Since yc is less than y and less than normal depth, our actual depth of 3.2 sits between critical depth and normal. So this is zone 2 of a mild slope. This is an M2 drawdown curve. The depth is getting shallower as it flows downstream. The flow is also approaching critical depth, accelerating as it goes. And one of the important tip that I can suggest you is to always compare three depth, that is y actual, y critical, y normal, and the relationship between these three tells you everything: the channel classification, the zone, and the flow behavior. And now let's start problem 4 part A. A rectangular channel of 10 feet wide uh, has 1300 CFS flowing at 8 feet deep. It expands to 12 feet with a new depth of 7.5 feet. We need the force on the walls of the transition. So for the first step, we can compute area and velocity. And let us write some given things for rectangular channel, that is upstream. We can consider above this as upstream and below this as downstream. For upstream, B1 is equal to 10 feet, Q is equal to 1300 CFS, Y1 is equal to 8 feet, and downstream, B2 is equal to 12 feet, and Y2 is equal to 7.5 feet. Now compute the area and velocity. So our area will be B1 into Y1 since it is rectangular channel, so it will be 80 feet square. And since we compute area, we can compute velocity as well using continuity equation. Similar things was done for um, downstream as well. So from that we could get B2 as 14.44 and B1 as 16.25 feet. And let us write some constant like that will be used in later part. Specific weight of water value will be equal to 62.4 lv per feet cube, and gravity acceleration due to gravity will be is equal to 32.2 feet per second square. And now let us compute the hydrostatic force, hydrostatic pressure forces. So for a rectangular cross section area, so hydrostatic force will be equal to 1 by 2 specific weight of water times width times depth. So our P1 will be, since we know this as well, we know B as well, we know Y as well. So for the P1, for the upstream part, so since our B1 is equal to 10 and our Y1 is equal to 8, so we get like P1 is equal to 19,968 lb. And similarly for P2, pressure 2, we get 21,060 lb. Now let us apply the momentum equation. So we will be using the uh, force balance in the direction of flow from left to right. So P1 minus P2 plus F walls. So I have chosen this as plus now, and I explain why I choose this. And this F walls tells me the force the transition walls exert on fluid, and this density is equal to rho by G. And when we solve, we get like F wall is equal to minus uh, 3468 lb. This negative sign tells us walls are pushing upstream against the flow direction, and by Newton's third law, water pushes on the walls with an equal and opposite force of same force, that is 3468 pound in the downstream direction. And here the sign convention matters here. If you assume wall force is positive in the downstream direction and get a negative answer, the force is actually upstream. Always state both what the walls do to the water and what the water does to the walls. And you might get confused on this, so you need to take care about this. And our second part will be computing the energy dissipating ramp. So it is given like a rectangular channel is flowing at a velocity of 28 feet per second. So velocity is given, and it has a ramp to take out the energy in the flow. And the question asks us to find the amount of power lost and force on the ramp per foot of width of the channel. So given parameters for upstream, velocity is equal to 28 CFS, depth is 2 feet, and for downstream, Y2 is 5 feet. And some of the constant are this specific weight is 62.4, density of water is this specific weight of water divided by G, which will be equal to 1.94 slope per feet cube. Gravity is also given, and we will analyze flow per foot of the weight, that is we assume B is equal to 1 feet, 1 foot. So first let us compute the flow rate and downstream velocity. So the discharge per unit width remains constant. So our Q will be equal to B1 into Y1 equal to 28 into 2, which will be equal to 56 CFS per feet. So why I have done this is because of this continuity equation. So I just divide by B and I get this one, which is discharge per unit depth. And we can find velocity at section 2 as well. Since we know the Q, this Q and v2 times y2 will be equal to this 56, so that help us to determine velocity at section 2, which will be equal to 11.2 feet per second. So our specific energy and our specific energy and energy loss. So let us find the energy at section 1 separately and section 2 separately, and then difference it to find the energy loss. So for office stream, energy will be equal to y1 plus b1 square divided by 2g. We know b1 as well. And similarly for downstream, we will be using the formula y2 plus b2 square divided by 2g. That gives us 6.9 feet for E2, and for E1 it is 14.2. And when we compute energy head loss, that is daily, it will be equal to 7.25 feet. And similarly, we can also compute power loss. So it will be equal to rho times Q times daily. So since we know this specific weight of water as well, we know Q as well, we know daily. So when everything is here, we just put the number here uh, in the equation, and we get 25,334.4 feet lb per second per feet. And when we convert that into HP, it will be equal to 46 HP per feet. So let us compute the force on ramp using the momentum equation. See, the momentum equation will be equal to P1 minus P2 minus F ramp, which will be equal to density times Q B2 minus B1. And we compute like F1 and F2 separately, and at last we get like F ramp is equal to 1168 lb per feet, and our force on ramp is 1168 lb per feet per width, and that acts as downstream. That is, the water pushes the ramp in the flow direction with 1168 pounds per foot. And always check that your answer makes physical sense. The ramp shows flow down. The ramp slows the flow down and increases depth. So the water must be pushing against the ramp in the flow direction. If your force came out in the wrong direction, check your sign convention. And this is what I already mentioned and talked. And before I finish, I want to recap what we covered. So in the problem 1, we covered water surface profile. Remember the three questions: mild or steep, which zone, and what caused it. And for problem 2, we talk about circular pipes, and always compute Q first, Q full first, then use the hydraulic element chart. And problem 3, that is trapezoidal channels. We use heat and trial for computing the alternate depth, critical depth, and normal depth. And for problem 4, we use momentum, and you need to draw your control volume, identify all forces, and watch your sign convention.